Welcome to Online Precalculus. This is section P.9, Linear Inequalities and Absolute Value Inequalities. So the objectives for this section are to use interval notation. Then we'll find the intersection of unions of intervals with interval notation as well. Then we'll solve our linear inequalities, compound inequalities, and absolute value inequalities. So first, let's take a few minutes to talk about interval notations. And this is just a way that we can represent sets of numbers. So suppose when we look at these that A and B are two real numbers, and then A is always going to be less than B. So if we're looking at a number line, A is my first number, the smaller number, B is my greater number. So we have four types of intervals that we want to look at. First is an open interval. And this represents the set of real numbers between but not including A and B. So basically we're saying that X such that A is less than X and X is less than B. And you can notice that we use parentheses for this open interval. Okay? Another way to think about the graph is that this would represent two open circles at the end. So instead of putting the open circles, we can put on the number line the actual interval notation symbol, so a parenthesis or n square bracket, which is part of the closed interval. So the open interval, you can see that these are less than signs, but with a closed interval, you now have less than or equal to symbols. So in my closed interval, A, B represents the set of real numbers between and including A and B. So up top, not including, and these include the endpoints, or it can be thought of as a closed circle. Okay? And again, we can use the symbol for my set, which is the brackets, instead of the closed circle or the open circle. And then we have our infinite intervals. And infinite intervals represent the set of real numbers greater than A or less than A, or greater than or equal to B, or less than or equal to B. Okay? So for my infinite interval, we are always going to have the infinity symbol. And the infinity symbol does not represent a real number. It just means that the line keeps on going. It indicates that the interval extends indefinitely to the right or left. And because you can never actually get to infinity, we're always going to use parentheses when we have the infinity sign. If my graph extends to the right, it is infinity. If it extends to the left, it is negative infinity. Okay? And then depending on whether or not I have greater than or less than, or greater than or equal to, less than or equal to, we use the parenthesis or the square bracket to say whether or not it is included or excluded from the interval. Like I just said here, parentheses indicate the endpoints are not included in an interval. Square brackets indicate endpoints are included in an interval. Parentheses are always used with infinity or negative infinity. Okay, so here's the 9 possible types of intervals used to describe sets of real numbers. And we have our interval notation and our set builder notation and the picture. So with parentheses, A comma B means X such that A is less than X, which is X is less than B. And we can see my graph with 2 parentheses, and we're just filling in the space between A and B. That's what it means, right? It means that X is everything in between A and B. With 2 brackets, it means X such that A is less than or equal to X, which is less than or equal to B. And again, we fill in all the space between A and B. And then we can just change the side that the parenthesis is on. Notice that I have a parenthesis in the second term and a second term on my set builder notation. First term in my set builder notation. So the parenthesis indicates that it's not or equal to. My infinite intervals, where A is not included, so that's X such that X is greater than A. and then one where A is included versus X such that X is greater than or equal to A. So we have our parenthesis and our bracket depending on whether or not we want that to be equal to. And those are extending to the right. And then we can do the same thing with less than, and I use negative infinity, comma B. My interval notation, always the first term, the term to the left is where my graph starts, and my term to the right is where the graph stops. We always read these graphs left to right. And then finally, the last one is the set of all real numbers. So that goes from negative infinity to positive infinity. Okay, let's express each interval in set builder notation, and then let's graph them. So first, to put it in set builder notation, right, we're saying x such that x, we have a parenthesis, so that's, whoops, -1 is less than x, which is less than or equal to 4. Okay, because I have a parenthesis and a square bracket. If I'm going to graph that, I'm going to put a parenthesis and a square bracket at 4, and I'm going to color in the space between them. Okay, we'll use a red. Color in the space between it. So here's my graph. Okay. For B, my set builder notation is x such that 2.5 is less than or equal to x, which is less than or equal to 4. And as I go to graph this, we'll use the red again. 2.5 is about right there, so we're going to use that's 1.5, 2.5, bracket at 2.5, bracket at 4, and I just color in the space between them. Negative and 4 to infinity. So now my set builder notation is x such that -4 to infinity. So we're saying that x is greater than -4, not equal to, because there's no square bracket. And we start at -4 with a parenthesis, and my graph goes to infinity. We can do these real quick. Set builder notation. Let's do set builder notation for all of them. X such that -2 is less than or equal to x, which is just less than 5. And then x such that 1 is less than or equal to x, which is less than or equal to 3.5. And finally, x such that x is less than -1. Okay, and then if I were to graph these, we would go from -2 with a bracket to 5 with a parenthesis. There's my first graph. And then 1 with a bracket, 3.5 with a bracket, and there would be my second graph. And finally, -1 has a parenthesis, and my graph keeps going that way. Okay. All right, so next we can make a intersection and union of two intervals. So in section P1, you learned how to find intersection and union of sets. Recall that we have a symbol for intersection and union. Intersection means what's common between both sets, where they overlap. And union means put both sets together, so everything in A and in B. And because intervals represent sets, you can find their intersections and unions, and the easiest way to do that is to graph them. So graph each interval on a number line, find the intersection, take the portion of the number line that the two graphs have in common, union, put them both together. So when I have two graphs, So I'm going to just graph both of these pieces. So let's graph from 1 to 4 with parentheses. I didn't put another color up here. Let's just put blue. And then from 2 to 8 with brackets. And now I want my answer to be the intersection of these two. And you can see, just in black, that from here to here, they overlap. So the answer is 2, 4 parentheses. And that is the intersection of the two graphs. When it says union, right now we're just putting them both together. So now, we'll start with blue this time. We're going from 1 to 4 with parentheses. And then with red, we'll go from 2 to 8. And so my answer becomes everything on this graph. So it goes from 1 to 8 with a bracket. Let's try again. Intersection of 1, 2, 3, 2 to 6. And you can see that my intersection is from 2 to 3 with a bracket. And that was the same thing. I should have just kept it. 1, 2, 3, and 2 to 6. The intersection, or the union, would be from 1 to 6. Furthest to the left to the furthest to the right. Intersection where they overlap, union, put them both together. Okay, so now let's start solving linear inequalities. We know that linear equalities, or linear equations in x can be expressed as ax plus b equals 0. And in inequality, we're going to express it the same way, only now we have 4 choices: less than or equal to, greater than or equal to. Each in the form where a is not 0, or else we don't have a linear inequality, we just have a plain old inequality. So let's look at the question that was in the intro to the section that I didn't cover. So how many miles could you drive a rent-a-heap car if you can spend at most $335? And there was an equation for that because the question actually said that the weekly charge is $125 a week plus 20 cents a mile to rent their car. Okay, so you can see that you're charging $125 a week plus 20 cents a mile to rent their car. And we want to spend less than or equal to, right? That's what it means, spend at most $335. You want to solve this? We're going to solve it just like solving an equation. Okay, so our goal is to get x by itself on the left side. So you would subtract 125 from both sides. And then once you isolated the 0.2, we divide out the 0.2 from both sides. And we get 1050. So with $335 to spend, you can travel at most 1,050 miles. So we started with an inequality and obtained x is less than or equal to 1050 in the final step. These inequalities have the same solution, namely x such that x is less than or equal to 1050, or in interval notation you would say sort of negative infinity to 1050, okay? But for this particular problem, this doesn't really work because you can't drive negative infinity miles. So I would argue that it would be from 0, including 0, right? We could drive 0 miles. 0 to 1050 would be the usable domain, but you get the idea there. And all these solutions, right, all the equations, inequalities like this with the same solution set are said to be equivalent, right? That's how we solve any equation. That's how we solve any inequality. Just keep getting equivalent equations until we have isolated our variable. when we isolated x here, we divided by a positive number. Okay? Let's consider the inequality when we divide it by a negative number. Okay, so first think about this. 10 is less than 14. Makes sense. Now let's divide both of those by -2. So 10 divided by -2 is -5, and 14 divided by 2 is -7. But we're saying that 10 was less than 14, but now clearly -5 is greater than -7. So notice that the direction of the inequality symbol is reversed. And this is our most important point for solving an inequality. And it says that when you multiply or divide both sides of an inequality by a negative number, the direction of the inequality is reversed. And that is called the sense. Okay? So when we multiply or divide both sides by an inequality, by a negative number, you have to change the sense of the inequality. So, what properties can we use to isolate the variable? Well, same as if we had a regular equation. We could add something to both sides. We could subtract something from both sides. We could multiply or divide by both sides if the multiplication or division is positive. And if it's negative, notice that we go from less than to greater than, less than to greater than. We change the sense of the inequality if you multiply or divide both sides of an inequality by the same negative number. So let's solve and graph my solution on a standard number line. And we can do this pretty simply, right? We just isolate the variable. So this is -2x is less than or equal to 8. Divide both sides by -2, which means we now have to reverse the sense of the inequality. To graph, we simply make a number line. -4, -3, -2, 1, 0, 1, 2. Can make it as small or as big as you like. And we say that x is greater than or equal to -4, which means we're going to use a square bracket. And my number line looks like that. In interval notation, my interval is from -4 to infinity. Let's try another one. Same idea, isolate the variable, remembering that if we multiply or divide by a negative number, you must change the sense of the inequality. So this turns into 3. We are dividing both sides by a -3, which means we change the sense of the inequality. My number line, x is greater than -1 or equal to, so there's my graph, and my interval is from -1 to infinity. Here's another one. Same sort of idea. Now we have variables on both sides, which is perfectly fine. Typically, you want to collect the variables on the left. Makes it easier to graph the inequality, but you might not like to do that because maybe you want to keep the variable positive. So if you add 2x to both sides, we're never going to have to divide by a negative number, but at the end you're going to have to flip the inequality again to put the variable on the left to make it easier to graph. I usually just like to collect them all on the left. It's greater than 5. Add 4 to both sides, so that's -3x is greater than 9. And then when I divide both sides by -3, I just remember to reverse the sense of the inequality. My graph, 0, -1, -2, -3, okay, 1, whatever, because we're going to go to the left. And so my graph looks like that. My interval is from -infinity to -3 parenthesis. Solve and graph. Again, I'm just going to bring everything to the left to keep it nice and easy. So that's -4x plus 1 is greater than -15. Subtract 1, -4x is greater than -16. Divide both sides by the -4, and so x is less than +4. My graph, I'm just going to put the 4, 5, 3. Less, no equals, so we're going to look something like that. And my interval goes from -infinity to 4 with a parenthesis, not a bracket. If your inequality contains fractions with consonants in the denominator, begin by getting rid of the fraction, multiply by the least common denominator. Okay, easier to solve equations when there are no fractions. So multiply everything here by 12. Okay, that turns into 3 times x plus 3 is greater than or equal to 4 times x minus 2 plus, 3 times, well, in this case, it'd just be 1. So we have 3x plus 9 is greater than or equal to 4x minus 8 plus 3. Combine like terms. So we have 4x -8 plus 3 is is a -5. Okay, subtract 4x from both sides, that's a -x. Subtract 9 from both sides, we have -x is greater than or equal to -14. Divide both sides by a -1, and we have x is less than or equal to a positive 14. To graph this, I'm not going to make a whole number line. I'm going to keep this nice and easy. There's a 14, 13, 15, and x is less than or equal to, means a square bracket, and we have our graph like that, and our interval goes from -infinity to 14 with a bracket. Let's try one more, just like that. Easier, 2, 3, 6. Common denominator between 2, 3, and 6 is 6. So that's 3 times x minus 4 is greater than or equal to 2 times x minus 2. And then the 6's just cancel, so we have a plus 5. 3x minus 12 is greater than or equal to 2x minus 4 plus the 5 is greater than or equal to 2x plus 1. Ooh, look, when I subtract now, I don't have to reverse the inequality because I don't have to divide by a negative number. Okay? My graph is x is greater than or equal to 13, so we're going to go this way. My interval is from, not a parenthesis, square bracket from 13 to infinity. All right, so next comes compound inequalities. And let's consider two inequalities like -3 is less than 2x plus 1 and 2x plus 1 is less than or equal to 3. And you can smush these two together to make a compound inequality, like -3 is less than 2x plus 1, which is less than or equal to 3. And you don't have to write the word and. The word and does not appear when the inequality is written in its shorter form in this compound inequality. You always start with a smaller constant, smaller one to the left, and then your variable terms in the middle. And even though the word and does not appear, the intersection is implied. We're saying that 2x plus 1 is in between -3 and 3. The shorter form enables us to solve both inequalities at once by performing each operation on all three parts and to isolate x in the middle. So let's actually solve this. So I'm just going to subtract 1 from all three sides. So now we have -4 is less than 2x, which is less than or equal to 2. And now when I divide everything by a positive 2, I get -2 is less than x, which is less than or equal to 1. To graph my solution, I have -2, 1, 0, 1, 2. We have a parenthesis there, a square bracket there, and we're saying that x is in between these two numbers. In interval notation, it goes from -2, whoops, like that, -2 to 1. Okay. But the idea here is that we can take this inequality and instead of solving it twice and seeing where the two graphs overlap, we can do this at once with the compound inequality. Okay. That number line got a little squished. Okay. All right, so again, let's subtract 3 from everything. So that's -2 is less than or equal to 2x, which is less than 8. And now we divide everything by 2. -1 is less than or equal to x, which is less than 4. Okay, my number line, crooked number line, -1, 4, 0, 1, 2, 3. Okay, and we go from -1 to 4 in between those 2 points. My interval, -1 to 4. Next, we'll talk about inequalities with absolute value. We know that the absolute value of x describes the distance of x from 0 on a real number line. And we can use a geometric interpretation to solve an inequality like x is less than 2. This means the distance of x is less than 2. And if we were to draw that, I didn't copy the figure, but if we were to draw that out, right, the distance has to be less than 2. So we could go between these 2 points would be the answer. Anything in that region right there, the distance is less than 2. So the interval shows that the values of x lie less than 2 units from 0. So x can lie in between -2 and +2. So x is greater than -2, right? Greater than -2, but less than +2. And we can write that with our interval notation, with our set builder notation. And now we can see that inequalities use that was using the less than symbol. Sometimes we have to use the greater than symbol. And with x is greater than 2, that means that the distance of x is greater than 2. So when I draw that one, let's make this one a little bit bigger. When I draw this one, 0, 1, 2, right, -2, so that means that the distance has to be bigger than 2, greater than 2. Well, that means it's going to go this way and also this way. So that gives us 2 sets of answers as well. And we can write that as x is less than -2 or greater than +2. And you could write an interval notation with the union of the two. Okay, so that suggests something to us about absolute value inequalities. If you have a less than inequality, you're going to have a and inequality, a compound inequality. If you have a greater than inequality, you're going to have an or inequality. It works both for a less than and less than or equal to, either way. The trick that I like to use to remember this is that if you overly enunciate your your inequality symbols, it can give you a little mnemonic trick to help you remember which type of inequality you're going to be dealing with, an and inequality or an or inequality. If you overly emphasize that inequality symbol, less than and less than, sounds like there's an and in there, gives me an and inequality. Whereas this one, if we overly enunciate it and say greater than, sounds like there's an or in there. Okay, so less than and inequality. Greater than or inequality. Okay, and that way we can use to remember which one is which when we are trying to set them up and solve them. So let's solve and graph the solution. It is a less than inequality. So that means instead of just writing it as, well, if I wanted to solve it and drop the absolute value bars, I could just say x minus 4 is less than 3, and x minus 4 is greater than negative 3, right? The steps to solving absolute value inequalities is in the negative case, always just reverse the sign. But I can see that those middles right there are the same, and if I reverse this, right, now I could just slide this piece and this piece together and write it as negative 3 is less than x minus 4, which is less than positive 3, and now I can solve these together. Either method works. Your text likes to combine inequalities into one. So we're going to just add 4 to all three sides and get 1 is less than x, which is less than 7, which means my answer is from 1 to 7 on the graph, 1 to 7, parentheses, and shade the region between them. Okay. So let's set that up without even, we'll skip the first step. We're not even going to write the and inequality. We can just go negative 5 is less than x minus 2 is less than 5. Right? I know I'm going to use the positive case and the negative case. I know it's a less than inequality, which means it's going to be an and inequality, a compound inequality. And now I can just solve it by adding 2. So that's negative 3 is less than x, which is less than 7 again. Okay, so now my graph goes from negative 3 to 7 and colored in all between. Again, my graphs are a little lazy, not putting all the points on there, but we get the idea. So that's from negative 3 to 7 in interval notation, which is usually how I would want to write this anyway, unless the question specifically said to graph it. Okay, so next, let's try another inequality here. All right, first, like most absolute value problems, we have to isolate the absolute value first. So I'm just going to move this over here so I have more room. Negative 2, 3x plus 5. Subtract the 7 from both sides to give me negative 20. When I divide both sides by a negative, you still, like any other inequality, have to change the sense of the inequality. Okay? And now we can decide whether or not this is going to be an and inequality or an or inequality. Right? Not until the absolute value is by itself, even though we reversed it, right? We did it before the absolute value is by itself. So this is an and inequality. So I can just go ahead and set it up as negative 10 less than or equal to 3x plus 5 is less than or equal to 10. Okay? Or I could have said 3x plus 5 is less than or equal to 10, and then the word and 3x plus 5 is greater than or equal to negative 10. When you're solving inequalities, absolute value inequalities, when you consider the negative case, you always reverse the inequality sign as well. This way is a little more compact. So negative 15 is less than or equal to 3x, which is less than or equal to 5. Divide out the 3, and we get negative 5 is less than or equal to x, which is less than or equal to 5 over 3. Interval notation for my solution is from negative 5 to 5/3. Right? And then we could put that on a graph as easily as the rest. Okay? Let's actually do the longer way with this one so we can check and see the difference. First, of course, is to isolate the absolute value before we do anything. That doesn't change, which is greater than or equal to negative 39. Divide out the negative 3, and we have 5x minus 2, 13, is less than or equal to a positive 13. Okay, so if I wanted to do this the longer way with the word and, I would say 5x minus 2 is less than or equal to 13, and, because it's a less than inequality, 5x minus 2 is greater than or equal to negative 13. Then I would have to solve it separately. So 5x is less than or equal to 15. Divide the 5. X is less than or equal to 3. And then I would do it over here as well. So 5x is greater than or equal to negative 11. So x is greater than or equal to negative 11 over 5. Okay? And then because it's an and inequality, my answer is only where those two graphs overlap. And it goes from negative 11 over 5 to 3. And they do overlap. If you think of the graphs, right, this is 3. It's going this way. This is negative 11 over 5. And it's going that way. So yeah, they will overlap in between the two. I don't like the way this is written. Okay, so I would, of course, switch it to 5 minus 2x, and the inequality still has to open the same way in order to be equivalent, right? So when I flip it around, I have to flip the inequality as well. And now we have a greater than inequality. Now there's no way to combine these two. We just solve it twice, and it's greater than, so we put the word or. 2x is less than negative 7, right? And that's my method to solve these, is I use the positive case with the same sign, the negative case with the opposite sign. Isolate the variable, is greater than 2. Divide by negative 2, you're still gonna do the same thing. You're still gonna reverse the sign in the sense of the inequality anytime you multiply or divide any time in this inequality by a negative. So negative 2x is less than 12, negative 12. Divide out the negative 2, and we have x is greater than a positive 6. Right, this is an or inequality, so my graphs are going to go different directions. And you can see that x is greater than 6 and x is less than negative 1. With my interval notation, I'm going to say this graph goes from negative infinity to negative 1, parenthesis, union 6 to infinity. Two separate pieces to the graph. Okay. And let's do one more of these. So same idea. I don't like the way this is written. So I'm going to take this and go 6 minus 3x is greater than 18. It is a greater than inequality, not a less than inequality, right? I always put my variables to the left. So we have 6 minus 3x is greater than 18. That's the positive case. Or 6 minus 3x is less than negative 18. Subtract 6 from both sides. Negative 3x is greater than a positive 12. Dividing out the negative 3, remember to change the sense here, and I get negative 4. On the opposite one, we get negative 3x is less than negative 24. Dividing out the negative 3 gives me x is greater than a positive 8. On my number line, we have a graph going to the left, a piece going to the right. My interval is from negative infinity to negative 4, union 8 to a positive infinity. Lastly, we can use inequalities to help us solve application problems, to help us solve word problems. Acme Car Rental Agency charges $4 a day plus 15 cents per mile. Interstate charges $20 a day, 5 cents a mile. So obviously, if you think about this, cheaper if you drive less, more expensive, but more expensive to start, but the more you drive, the cheaper it's going to be. Okay, so eventually, because it's paying 5 cents and 50 cents, eventually interstate is going to be cheaper, but it doesn't start out that way. And that's the question. How many miles must be driven to make the daily cost of Acme rental a better deal than the interstate rental? Okay, so I want to know when, so we have $4 a day plus 15 cents a mile. Okay. How many miles must be driven to make the daily cost? Okay, so I want Acme to be a better deal. So the Acme char rental car. So we're going to say, when is this true? When is this cheaper one going to cost less than the $20 a day and 5 cents a mile? Nothing much here to do except isolate the variable, do the same things we usually do. Subtract 5 cents times x, subtract the 4 from both sides, and we get 0.1x is less than 16. Divide it out, and so x is less than 160. So if you drive less than 160 miles, the $4 times 15 cents a mile is cheaper than the $20 times the other one, right? If you drive 160 miles, they are exactly equal. Let's do one more. Car can be rented from the basic rental for $260 a week with no extra charge for miles. Continental, $80 a week plus 25 cents for each mile. How many miles must be driven a week to make the rental for basic a better deal? So same thing, we want 260 to be less than $80 a week plus 25 cents a mile. This one's nice and simple because I don't have any variables on the left-hand side. So we get 180 is less than 25 cents times x, divide out my 25 cents, and 720 has to be less than x. So as long as so if you drive more than right, 720 has to be less than x. So if you drive more than 720 miles, right, if I reverse this, 720, right, because this starts off a lot cheaper, right? Continental charges $80 to start, while this guy charges 260. So if you drive more than 720 miles, then the basic rental will be cheaper. And that was section P.9, linear inequalities and absolute value inequalities.